Good afternoon, everyone, and welcome. Thank you for joining in today's talk. So today I want to, first of all, let me share my screen. It's this one, I think. There we go. You can see correctly, right?
Yes, we can.
You can see full screen?
Yes.
Yes.
Okay, perfect. So, welcome everyone. Thank you for joining in today. So today I will be talking on a project I'm currently working on with Carlos Mendez Guerra and Lisan both from Nagoya University. This is currently we're still working on it, so any comments or suggestions are more than welcome. This work is titled Space-Time Dynamics of Pollution and Income in China. So as most of you are probably very well aware of, in recent times, as China saw this dramatic increase in economic growth and development, it went hand in hand with also a rather high increase in pollution and environmental deterioration. According to the WHO, this pollution, the population actually has been exposed to high levels of pollution, such as in the form of PM 2.5, which is basically particle matter, which is a very small particles that can actually 2.5, particle matter 2.5, which is actually very small particles that can actually affect our breathing and cause other health issues. And the WHO considers that the levels at which most of the population are exposed to are actually not very healthy. So in the year 2013, actually, the Chinese government implemented a policy to try to reduce air pollution. And by the year 2017, it actually was able to reduce by about 22.7% the environmental pollution, but from a particular type of particle matter, that is PM10, not PM 2.5, which had set out to actually reduce too. We observe in this graphs below basically the distribution of particle matter 2.5 for both the year 2013, the year of the implementation of the policy, and for the year 2018, which is a year after this was shown, these results were shown. And we see that the median at the year 2013 and the median of 2018 hasn't actually changed very much, actually has slightly, ever so slightly increased. And this actually tells us that, well, sadly, it seems that the policy has not been sufficient or strong enough, at least, or more measures probably had needed to be used so that the situation would have gotten better. Okay, so basically, before moving along, very slightly, there's actually quite a large literature on this relationship between the economy and the environment. A very common type of analysis is that of the so-called environmental Christmas curve hypothesis, or EKC. The classical paper by Grossman and Kruger in 1991 basically found this inverted U-shaped relationship in which there's at the beginning stages of economic growth or development of a given country. Economic growth goes hand in hand with an increase in pollution. Then at a certain point of the inverted U-shaped curve, we find this tipping point in which different authors find that depending on the country or depending on the analysis can be all the way from 20,000 US dollars in per capita income and above. In some cases, it requires higher levels of income for this relationship to revert. And then after that, more economic growth, is translated into reductions of environmental deterioration. At least that's what the hypothesis says. There's been lots of analysis and studies using this type of hypothesis for the case of China in recent years. And another strand of the literature is that of convergence of emissions of pollutants. Basically, different authors study whether there's a convergence in levels of pollution as the economy develops, either in certain regions or even between countries. And in this year, actually, a very recent paper by Wu et al. Analyzes 285 Chinese cities for the period that goes from the year 2000 all the way to 2018. What they do is they use a joint distribution analysis, and they examine the long-run relationship between income and PM2.5 concentrations. This work actually stimulated our interest in analyzing this. But what we were interested in doing is by using their data set to study whether there's a relationship also between income and air pollution, but from a spatial distribution point of view. Okay, so we used the 285 Chinese cities for this period that they have, and we wanted to detect if there are clusters of pollution and what their spatial dependence at the city level is. Okay. Additionally, we not only do we do this for the whole period from 2000 to 2018, but also we partition the period into two parts: the before and after 2013. That is the year in which this policy was implemented in China, to see what happens, right, with the clusters. Additionally, we were interested in seeing it not only from a static point of view, but also from a dynamic point of view. What is the coevolution of this income and PM2.5 emissions throughout the time period? Okay. Basically, the data, well, as I mentioned before, is for 285 Chinese prefectural and above level cities from the paper by Wu et al. In this data set, the air pollution and the income are actually normalized by dividing the values by their yearly average. So what we're working on is relative PM2.5 and relative income. What this does is basically shows us the distribution of how dispersed a given variable is from its mean. Okay, and we will say that the average works actually as a proxy for the national mean. Sorry. So basically, a given city, the values we will see for the given city will be if it's 1, 2, 3, or n times above or below from the national mean. What we do also is we use coordinates for the cities in order to spatialize this data. And this allows us to do additional analysis that were not possible that Wu et al. Had not performed before due to this inclusion of latitude and longitude. So before moving on, I think maybe many of the people in the audience are not familiarized with some of the definitions and terms that I will use. So very shortly, I will explain some of the concepts so that it's easier to understand and interpret the results. I mentioned before in one of the slides this keyword that is spatial dependence. So spatial dependence is basically what spatial dependence allows us to do is to capture what the relationship is for a given variable, say income or emissions of PM2.5 air pollution in a given location with respect to the spatially weighted average of the value of its neighbors. In other words, what spatial dependence allows us to do is to mutually capture what is the so-called locational attributes and attribute similarity and locational similarity. A given city with a given characteristic, and what is the relationship with its neighbors? Do they have the same level, similar levels of pollution? Do they have lower levels of pollution? And the same for income. As we see here in the three plots and the three graphs below, basically, we will say that there's positive spatial autocorrelation when, say, cities with high levels of pollution are also surrounded with cities or neighbors with high levels of pollution, and vice versa. Lower levels of pollution with cities with lower levels of pollution with cities with lower levels of pollution. We will say that there's no spatial autocorrelation when it seems that it's just randomly happening. So cities with high levels of pollution might be having some cities with also high levels and some with low levels. So no very specific pattern can be found. And vice versa, negative spatial autocorrelation will say what happens when, which is actually very rare in this cases, when cities with high levels of pollution or high levels of income are surrounded with those with the opposite effect or level, right? The gold standard to capture this or to measure this is the so-called Moran's I, which is an index which basically says that Well, we will have this variable wij, which is just a weighted matrix that positive values are telling us that there's a positive relationship between neighbors, and if it has 0 values, basically it means that there's no spatial relationship. Okay, and it's also row standardized values, so they all have to sum up to 1. The variable xi basically is the variable of interest that we're interested in analyzing, say income or pollution. For city I, xj will be the same, but for city j, and mu is just the mean. So how much is city i's value deviating from the mean, and the same for city j. In the case of Moran's I is an aggregated level, so it's summing up or adding up all city i's and all city j's. So if we're interested in capturing the so-called local Moran, which is what is the spatial dependence for a given city with respect to its neighbors, we just add each I with respect to all of its neighbors, j's. Also, I mentioned, sorry, before moving on, I mentioned this spatial weight, which is capturing the structure that these relationships are having. Well, if we're seeing that there's clustering or not. But we will say that when 2 spatial units share a border, in this case a city, we are interested in analyzing their contiguity, which is captured with this spatial weighted matrix. But how we define this is very important. So there are many ways to do this, but 2 of the classical ways to do this is through the so-called Rook contiguity or queen contiguity. For those of you who are familiarized with the game of chess, maybe this will be very easy to understand, but the basic idea is we will say that there's Rook contiguity when a given city is sharing borders, that is up, down, left, or right only with some cities. And this is simulating the movement of the Rook or the 2 towers, we will say in the game of chess, which only move up, down, left, and right. Or it's generalization, which is that of queen contiguity, that is showing the movement of the queen in the game of chess, which also can go up, move up, down, left, right, or also taking the vertices, the diagonal vertices. Okay, so queen contiguity we will say that there's queen contiguity when either any of the vertical directions, lateral directions, or diagonal ones are taken as neighbors. Other ways of taking into consideration contiguity can also be distances. So we will say that a given city is neighbor with another one if it's within a certain distance, in kilometers, miles, whatever we want to define. For this work, we use queen contiguity for the analysis. One last technical slide before we can actually move on to the results is that of Thiessen polygons. So this is a methodology that allows us to fix, in some way to say, when there are problems, say, with cities that are isolated or have uneven distributions, or it's not very clear who's neighbors with them. Basically, it's a way to generalize queen contiguity. What we do with this method is, as you see from the 2 graphs below, we can divide areas into subregular areas. So, for example, take this dot in the far left border. It's not very clear with whom it's neighbors, whereas the other ones seem to be more close or near each other. So by drawing lines that are exactly in between each of the dots, basically we can form a polygon-like shape, and it becomes much easier to interpret who is neighbors with whom by following the same definition of queen contiguity. Either they share one of the lines or the vertices, okay? And once we use this method and we plot it, say, in the case of China, we can more easily analyze which cities are neighbors with whom. And then we can also see the distribution, say, in this case of PM 2.5, and see that in this case, most of the cities with higher levels of pollution tend to be more in the middle or in the center of this ring-like shape that we find. Though that is, on the outside ring, we see more of the cities with lower levels of pollution, and the more into the middle we go, it seems to tell us that the distribution seems to tell us that is more located more towards the middle. Okay. Also, what we do is, given that I was mentioning before this environmental Christmas curve and the spatial dependence, we were interested in seeing first what the global spatial dependence was for the period under analysis. And we found this kind of S-shaped spatial dependence. It starts kind of flat, and then suddenly it increases, only then to reach, again, a kind of steady state. Nevertheless, we do observe that on the left, the y-axis, it's very interesting because we see that even from the beginning, there's very high spatial dependence. So we have values above 0.5, which it's telling us that, yeah, actually there is this effect, at least globally, that, yeah, cities with high levels of pollution might be clustering with other cities on average with other cities with high levels of pollution and vice versa. Additionally, what we do is we analyze also what the Gini is for all this period, and we call it spatial Gini because it's taking into context also the geography. And we even though it's not exact, we kind of find this inverted U-shaped relationship. It's not literal, but it helps us to kind of understand what is happening. And it would seem that at the beginning it increases and then it flattens and then it kind of goes down. But this is just for illustrative purposes. It's not, we shouldn't be taken so literal. Okay. So then what we finally do, moving on finally to the results, what we do is we analyze spatial dependence for the case of China for the year 2000 for PM2.5. In the graph to the leftmost part, we see the so-called Moran scatter plot. What this is doing is it's dividing the plot, the scatter plot, sorry, into 4 quadrants. The top top right quadrant, the so-called high quadrant, is telling us this cities that are in red are the so-called cities that are hotspots. That is, cities that are having high levels of PM2.5 that are surrounded by cities with high levels of PM2.5. Likewise, on the bottom left quadrant, the low quadrant is showing us the cold spots. Those cities that are having lower levels of pollution or PM2.5 that are surrounded also with cities with similar characteristics. Once we plot this through these polygons, we see that in the middle of this, once again, circular kind of or ring-like shape, we see that there are these cities that are clustering together with very high levels of PM2.5. And on the outside of this relation, we see these cities that are having lower levels of PM2.5 that are also having surrounded, with other cities with lower levels of PM2.5. I want to mention, I just noticed that actually there's a mistake here. It's not, the p-value here is not 0.1, it's 0.01. So it's at 1%. So this is only showing the colored, the hotspots and the cold spots are those that are statistically significant. Those that are in gray are actually not statistically significant. And this is shown, this line that crosses through the Moran scatter plot is telling us that the Moran's eye is telling us that actually there's high spatial dependence. And we also can see here on the right of all the plots, the kind of the relationship in China. It's very important to note, though, that we're not taking all the cities of China. So we're only taking those 285, and they're shown in white dots. And they are not, they're usually one per some provinces have one city and some have more. But basically it helps us to see that if we only consider China as those cities that we have data for, yeah, we can see that more towards the middle, the cities with higher levels of pollution are having neighbors also with higher levels of pollution, and the outside ones are having lower levels of pollution for the year 2000. When we analyze the same thing for the year 2017, once again, we see the Moran scatter plot, hotspots and the cold spots. Moran's eye is interestingly slightly higher than what it was before. Here it's 0.79, for the year 2017 is 0.83. Once again, we see the hotspots are in the middle of the ring-like structure and the cold spots on the outside part. And in the map in China, if you let me show you before and after, you see that there's kind of a movement from some cities, and they tend to cluster more towards that middle part. And the outside, once again, is showing us this relationship that more cold spots are appearing so far. Moving on, when we analyze the same thing, but for income, interestingly, the spatial dependence is not as high as before. It's still a little bit, there's still positive spatial dependence, but it's not as high. And we see that the hotspots are actually, in this case, on the outside, but interestingly, in the middle, we are seeing some clustering of cold spots with respect to income. Once again, these p-values are for 0.01. I will fix this in the future. And for the year 2017, once again, we see that some statistically significant cold spots are located more towards the middle, and the hotspots on the outside part. So if we compare this with the PM 2.5, well, we can see that there is kind of a relationship that cities with higher levels of income tend to have lower levels of PM 2.5, and cities with lower levels of income tend to be clustered with cities that also have lower levels of income and higher levels of PM 2.5. So at least statically, we are seeing kind of a, you could say kind of a poverty environment trap, in which cities with lower levels of pollution are trapped in this, also having higher levels of pollution, which can actually affect them and continue this kind of relationship throughout time. Okay. So up to this point,
I'd like to ask just one question.
Please.
When you measure income, do you sort of, well, and if someone works at the center and lives in suburb, which area, the income of which area do you measure? I think this data is kind of fine-tuned enough so that the CBS, CBD, and the suburbs are distinguished, right? And in that case, which area do you attribute the income to?
Right, that's a good question. So first of all, remember that we're only seeing a relative income. So how much it's deviating from the national average. But right. also we're taking only one given point. So it's not specifically to a suburb or not. It's just like the average of that area. So we cannot subdivide it whether it's that
I see.
From the suburb or not. At least with this data set, we cannot.
I see. So when you talk about the center and surroundings, it's bigger than the sort of the particular. You mean the sort of more abstract area than specific areas.
Exactly, as you mentioned. Right. Yes.
Okay. Thank you very much.
The city is where we have the data, but we're generating this fees and polygons, which actually are taking a larger area. So that's a shortcoming, I would say, from this data set.
I see. Okay. Thank you.
Thank you. If you have any other questions.
Yes. May I ask questions?
Yes.
So why are you considering creating polygon?
Well, we are using these polygons.
Why are you thinking about polygon rather than only like do not hold, like 2 kilometers, 3 kilometers, 4 kilometers? Because in the case of this polygon, some polygon will be 1,000 square kilometers and some polygon will be 1 kilometer.
Right.
So it's a different story, right?
Yes, that's a good question too. So we tried using distances, right? Like distance bands, but in some cases it's not very evenly distributed. So you would have to take very large distances for some cities that are a little bit more isolated. And what the result would be is that that city might have one neighbor and others would have all of the other cities being neighbors, or most of the cities being neighbor. And that affects a lot the analysis you can do. So by using these and polygons, it's a way of like regularizing slightly ever so much and being able to analyze more detail. If you take, say, some cities might be 500 kilometers away, and some cities might be 20 kilometers away. So if most
then
of
you should take, if you are thinking about like some cities are 20 kilometers away, it's better to take like 2 kilometers only and exclude everything.
But remember that
980,
we have so many cities.
990.
We have
Doesn't matter at all, because if you're thinking about this, because in some cities which are like you're thinking about one prefecture as the value, and in the case of some cities you are only considered 20 kilometers. So it's kind of, you are comparing apple versus oranges, right? Because if you are thinking about like only 2 kilometers of a city, everything will be more likely to be similar, right? So if you are thinking about like considering like 1,000 kilometers away, because there are not many cities which are 1,000 kilometers away. So that is why I was thinking like instead of like polygon, it's better to create like do not haul, like 1 kilometer only, 2 kilometers only, and then exclude everything.
Right.
That
Well, that's a valid question, a valid critique. We tried it, at least with certain distances, certain bands, because you have to have regularity in some way. Otherwise, you can actually say, oh, another way of measuring is saying, I want to have 6 neighbors, or everyone has to have a similar amount of neighbors. Otherwise, you always have cities that are isolated and you're losing values. So finding that optimal distance can be complex in some cases. And this is a simple way, at least, to find or divide this map as a grid. We will try. We're still working. So yeah, it's as you mentioned, maybe finding or working with different distances can also be an interesting way. Another thing that we're doing actually that I haven't mentioned yet, but we're enriching this data set and we're adding more cities. So that can also help also in the problems with distances. This is what we had at the moment what we were doing, but my co-authors are actually working and they seem to be being able to add maybe twice as many cities and for a larger amount of time. But at least for this analysis, that's what we had to do at the time. So yeah, that's a good point that you mentioned. Thank you.
And if I may ask another question, so what is the definition of a city?
Well, here is at the beginning, I mentioned, they define this Chinese prefectural and above level cities, those that are defined by the government to be those that have higher than certain levels of population, or that have certain, I don't know, like rankings or something like rating, like in China they have different rankings. So we are only taking those that for which data actually was available, which are the ones that are more important or more significant for the government.
So why I'm saying is that, for example, like if you are thinking about that, then Shanghai will be one city or will be 100 cities?
One city.
Only one city, right? So for example, if you are thinking about like above population, one, for example, Kitakyushu city, within Kitakyushu city, it could be like Tobata and Moji, and that could be considered as a city. So that is why I was thinking like if it's kind of above that level, then every cluster will be within Shanghai, there'll be many cities, right?
Right. No. It will be considered one city in this case. Yeah. If we can, we're trying to enrich it so that we can actually partition it or consider it in that way. But well, the data was done that way because it's some data is not available. So they had to use actually some proxies or some methodologies to approximate it and find it. And that's the best way that they could do it, it seems. So yeah. Let me go back here. Okay. Any other questions or comments?
May I?
Please, yes.
I have 3 questions. First one, I think I want to confirm like the reason you use PM 2.5 or PM 10 is because other pollution, the data is not available, right?
Yes, and also because PM 2.5 is actually one of the, most people use PM 2.5 with respect to PM 10 because it's a smaller radius particulate matter. So it tends to be more important to work with. And also, well, data availability. It tends to be usually more available with PM 2.5 than other pollutants.
See. And for the spatial correlation, I'm wondering why you only use Moran I, because in my memory, I think spatial correlation, you have like Watts test and also like LMERR test, like an LR, like they are all for like spatial correlation. So I'm wondering, is there any specific reason that you choose Moran I for the spatial correlation?
Well, it tends to be more, you're right. The Moran's eye actually captures very well certain things like this neighborhood effect, but also because of the software that we're using is mostly developed with that kind of methodology. I haven't seen the other methods that you were mentioning available in the software that we're using. So
yeah, because what I'm thinking is like if you can use different spatial dependence to test, and then if you receive the similar result, then your result will be more like robust.
So what you do basically is you test for the robustness of this by varying or changing, say, for example, the weighted matrix. So you try with different contiguities. You try with the root contiguity, you try with queen contiguity, with different distance bands, k-nearest neighbors, other methods. And then you try to see if it changes a lot or not the results that you obtain. That's one of the ways we test for the robustness, actually. Yes.
And related to the metrics you just mentioned, my third question is you use the contiguity metrics, right? And yeah. But I think there's the other metrics called distance metrics.
That's it. That's
you put the. Did you also try that?
Of course. That's what I meant. I use the k-nearest neighbors. So you can say within a certain distance, all those that are nearby. No, sorry, not the k-nearest neighbors is what's the minimum distance that anyone has to have in order to have a given number of neighbors, 5, 6, or 7. You take that for each of the cities. The other one is I only would consider some city to be neighbor with another one if they're within a 50-kilometer radius, 100-kilometer radius, or whatever. What we do is we use this queen contiguity and we compare it with the other ones also, and we see the results. Yes, to test for robustness. Yes.
Thank you very
much. Okay, any other questions? Otherwise, I can continue, and then at the end, of course, anyone who has further questions, we can continue if you want. So, okay, so up to this point, I've been talking mostly on static types of clustering or analysis, but we would also like to see what is the spatial coevolution of these two variables, income and air pollution, over time. So in order to do this, we use a different method, but that's called directional visa. The idea of this is it's instead of showing dots as representing the cities, it will show vectors of joint movement of cities and neighbors with respect to the variables of interest that we have. In this case, the vectors will be we will have the starting point, and we will see how the arrow shows us where it's moving towards a quad, like the scatter plot that I showed before. So a given city is moving towards which of the 4 quadrants, and also what is its relative position with respect to its neighbors. Don't worry, once we see the graphs, it will become much easier, but that's the basic idea. And the basically, if you see the functional, this index that we have, the functional form is very similar to that of the one we had, here, local Moran's, or of the Moran's even, Moran's eye. The only difference is, instead of being static, we add a time, a t variable here, so that we see how much the pollution for city I at time t represents with respect to its mean. And the same for city j. The hypothesis that we test in this case, the null hypothesis, that a given city will move to a certain quadrant, but it's independent from the movement of those of its neighbors. It's just by random chance or whatever that they tended to move towards that quadrant. It does not have to do with an effect from its neighbors and vice versa. Whereas when we reject the null hypothesis, we will say that no, a city is moving to a quadrant because of the mutual effect with its neighbors also moving towards that quadrant. Okay. In the very simple terms here, we can do the comparison of the static and the dynamic Moran scatter plots, right? If you remember in the static case, when we saw the top right quadrant, the high quadrant, basically we would see cities with high levels of income or high levels of pollution that are also surrounded with others with high levels of income or pollution. And in the low quadrant, in quadrant 3, we saw cities with lower levels of a given variable surrounded by cities with also similar type of attribute or variable. In the case of the dynamic Moran scatter plot, in this case, it will be either cities or regions that are moving upwards that are surrounded also by cities that are moving that way. Okay, same for the low quadrant. And in the case of quadrant two and quadrant 4, which is top left and the bottom right, we will see that cities are with high levels of income or high levels of pollution are moving to a quadrant with cities that have lower levels of that given variable, or vice versa. Okay. Here, it's much easier to see. We see first that, first of all, what we do is we divide cities into 3 groups: East, Central, and West, with respect to the relative PM2.5, the variable that we were using. We standardize this directional Moran scatter plot so that they all start from the same point. Otherwise, we would have arrows from going all different directions, and it becomes more difficult for the eye to interpret what is happening. Basically, what this is showing us is that, well, cities in what was the east side are on their majority moving towards the high quadrant, implying that their pollution has been increasing from the year 2000 to 2017. And those cities in the west quadrant are mostly moving on the low quadrant. That is, they've been reducing their levels of relative PM2.5. The case of the cities in the central area, it's more ambiguous. Mostly they tend to be clustering towards the high quadrant, but we do see some that are not. So it's a little bit it's not very clear in this case. But nevertheless, we do see this kind of polarization or partitioning between East and West for this period under study. When we do the same for the relative income, we see the opposite effect on average, right? Cities on the west are moving towards a high quadrant, and cities on the east tend to move to the low quadrant. So when we compare this with the previous one, we will say that, well, cities whose PM2.5 has been worsening, their income levels also have been worsening. And cities whose income has been increasing relative to the average have seen a decrease on their emissions on average for this period under study. Okay, but now when we analyze this by partitioning the period into 2, before and after this policy from the year 2013, we see that in the first period, yes, on average, it's still the same behavior occurs. East continues going towards the high quadrant, west moving towards the low quadrant, central cities mostly also along with the east quadrants. But the interesting thing is, on the period after the intervention from the government, we see that it's not very clear what's happened. It seems that cities that were clustering in the low quadrants, those from the west, now are in a large proportion also clustering towards the high quadrants. Cities that were in the east that were clustering towards the high quadrants, now some are moving towards the low quadrant, or also spatial outliers in the top left and bottom right quadrants. So the interpretation that we can give to this is that the policy the government implemented actually kind of altered this polarization, or altered this effects that were happening before. If this was intentional or not, probably it was unintentional, because cities that were improving actually seem to be worsening, which is something that I don't think the government would have desired to do. But so far, it seems that it has caused this kind of things. Also, we can see this arrow here, the city on the east. That's very interesting, where we can see that actually it's worsening in PM2.5 has come, whereas its neighbors actually are improving. So in some cases, it also has had unexpected results like that. So, well, we have not found yet a reason, but we think it's a very interesting and something to look more into detail. Some policy implications that we can talk about from these results that we see. First of all, of course, the more obvious one is that more work needs to be done to reduce PM2.5. As I have mentioned before, basically we see this diffusion patterns of pollution and income, and this can be shown here, right? What seemed to be improving in certain area has been altered, and certain things have diffused from one region to the other. So more work and more careful attention to detail might be needed to do so that this worsening in certain regions does not happen again. Also, by detecting clusters with this method, allows us for policy coordination at the cluster level. So basically what we can do is pinpoint at certain locations or certain regions where more effort needs to be taken. And we can actually go more into detail later and see even which cities particularly have gotten worse, by what magnitude, and which are their neighbors, etc. And we can contrast this between the static and the dynamic approach to see if results are similar or very different. So far, we've seen that on mostly the static and the dynamic approach have gone on the same way, have shown similar results. And another policy that we think that is very interesting is that of, well, collaboration between China and some of its neighbors, such as Japan. This is due to the fact that, well, some neighbors such as Japan have actually had similar experiences in periods of high economic growth with worsening or dramatic worsening of pollution. And in more recent years, Japan actually has been successful in reducing PM 2.5 to a certain extent. And we think that this collaboration can be mutually beneficial. Japan can provide China with some of its experience and some recommendations from its experiences, while at the same time Japan benefiting from the improvement in China due to the fact that, well, sometimes a lot of the pollution is transmitted through wind or other forms, and actually Japan suffers this kind of negative externalities. So China improving also benefits Japan by, well, this neighborhood effect not happening anymore. Mutual benefits that can be very good. Another thing that Japan can provide is its experience with the data gathering stations of PM 2.5. So Japan has in recent years, by increasing the number of stations that capture data or capture the amount of PM 2.5 on certain areas, it can also target more efficiently. And if China also probably increases its numbers of data stations, it can be successful in the same way as Japan has done. This, of course, takes time and a lot of effort, but it can be a very successful approach. So far, well, the conclusions that we can gather from this. First, the importance of spatial methods in order to analyze pollution-income relation. Okay, so the original paper that we talked on, they only analyzed conversions, but without taking this geographic dimension into account. We saw that there's a very high and significant levels of spatial dependence, very high meaning that it's higher than 0.5. And actually it's very significant that p-values are actually 1 or lower, below 0.01%. To the best of our knowledge, other authors do not discuss this spatial dependence or geographic case to the best of our knowledge. But of course, if anyone is familiarized with some literature and can recommend us or point us to it, we would be more than welcomed. We also saw this spatial dependence that changes through time. It shows this S-shaped relation, which is actually very interesting. Starts at a certain level, quickly jumps, and then stabilizes again. We're interested in finding out what causes this, because it follows this similar relation as diffusion of technology, in which at the beginning there are few adopters of the technology. Suddenly it accelerates, and then it reaches a certain point in which most or all of the population has adopted certain technology. We're not sure if it's due to a similar type of behavior or diffusion pattern, but it could be interesting to analyze. And finally, we saw the how this dynamic clustering is showing kind of like a polarization between East and Western China, at least for the whole period. But when we partition this period in two, before and after the 2013 intervention, we see that, well, the post 2013 period is a little bit more random. So that could be an interesting idea to analyze in more detail, or to try to explain why it's happening. we are, as I mentioned before, trying to gather more data to add into this data set so that we can enrich it. And hopefully with that, we can actually see in more detail if something is happening. If it's just not that this 285 cities have had some randomness in the middle and other cities can actually help a little more explain why it's happening. But well, that's something we're working on, and hopefully soon we can actually implement. So, well, thank you very much. If you have any questions or further comments, please, I would like to hear and reply to them. Thank you.